NASA's Earth Science Division, we study nearly everything in the Earth system, from the top of the atmosphere to deep underground, including oceans. NASA's Earth data systems, which hold data from Earth-facing satellites, have over 40 petabytes of data, or equivalents to about 13.2 billion songs, or about 100,000 years of uninterrupted songs on Spotify. So about machine learning and earth science, in NASA's Earth Science Division, our missions are about understanding our dynamic living planet. We use machine learning to help make sense of data from Earth observations and models. Some uses are for explainability or hypothesis generation, so think feature detection, uncertainty quantification, think modeling and analysis, and verification and validation. So consider the number of changes the Earth undergoes, from deforestation in the Amazon rainforest to a glacier melting in the Arctic, or to landslides in Puerto Rico. For the summer of 2022, I've been thrilled to work with a team on self-supervised learning on synthetic aperture radar data. I want to thank the entire team, their lead faculty member, Raul Ramos Poyan, our partners from the USGS, JPL, and Alaska Satellite Facility, and lastly, to all the FDL partners who helped make this summer a success.
Good day, everyone. I'm Ragini. Ivanis and me, we are super excited to share our team's 8-week journey here at FDL, where we have investigated how we can use satellite imagery to detect change on our planet using AI. I would like to introduce the Earth Science team. We like to call ourselves as the SAR. We are made of 4 researchers, Ivanis, Vanessa, Viji, and me, and we have an amazing team of faculty who have guided us at every step. According to the United Nations, landslide in the past 20 years has affected 4.8 million people and caused almost 20,000 deaths. The rising temperature and climate change is only going to make this worse and trigger more and more landslides. In such a scenario, it becomes really crucial to provide timely and accurate data for emergency responses and decision makers. In the aftermath of a disaster such as landslide, commonly optical imagery is used to map the landslide extent, which guides and informs the emergency interventions. However, optical imagery has its own limitation, as it cannot sense at night and cannot look through clouds. As we observe on the screen here, our beautiful planet is always covered with clouds. We require a monitoring system that is independent of daylight, cloud cover, and weather conditions. This can be achieved with SAR. SAR is synthetic aperture radar, an active imaging sensor. SAR has the superpower that it can send signals to the Earth and record back the reflected signals. With this superpower, SAR can see through clouds and work at any time of the day. However, the SAR images obtained are complex to understand. While optical images can be simply interpreted as photograph, SAR requires a different way of thinking in terms of wave signal to interpret its different products, such as intensity, phase, and coherence. Though SAR is complex, it is rich in information. Can we use AI to extract this rich information from SAR data? Yes. The first step towards this is to lower the barrier for non-domain and machine learning experts by creating ML-ready, analysis-ready data cubes. Creating these data cubes was not trivial, as it requires expert-level knowledge for pre-processing SAR data, sometimes even up to 19 pre-processing steps to arrive at the SAR bands that is stored in this data cube. The other key component of this data cube is the label, which requires high human effort to manually look through the landslides and annotate them. With our custom data pipeline, we were able to create 4 analysis-ready data cubes for different landslide events.
The question now is, can we use AI to automatically detect landslides from SAR data? We start our analysis in Puerto Rico, where Hurricane Maria caused a lot of landslides. The dataset we have includes point labels that are the top of the landslides. The landslides there are small and also in dense vegetation. This makes the problem quite hard. According to experts, it might be an impossible task. And it has been very hard indeed. Several of the approaches we tried didn't produce good results. Eventually, we managed to have a model that combines SAR data with elevation data and does produce landslide density maps of good accuracy. So now we can imagine that instead of having experts go to the field and measure the landslides to produce landslide density maps like this months after the disaster happens, we can instead use an AI model that gets the data from the satellite and produces quickly landslide density maps. So we have the satellite looking from the sky, not being affected by clouds, and feeding data to the algorithms that produce density maps like this. Now we move on to Hokkaido, Japan. There we had some landslides induced by an earthquake which caused great devastation. For this dataset, we have the full contours of the landslides. So here we use a different model. We use a segmentation model trained to identify these contours. And in the validation set, data that have not been used by the model during training, we see predictions that very well match the labels. Actually, we can also identify that fusing data again, the SAR data with elevation data, can help us in early detection, can help us in what we want for rapid damage assessment. Now we move on to self-supervised learning. The problem in remote sensing for natural hazards is that many times we have a scarcity of labels. So the idea here is to use the input data and learn from that. The framework that we use is called masked autoencoders. And the idea is the following. We get the original data, we hide a big percentage of it, and we make the model learn to reconstruct the input. The hope is that this allows the model to learn a good representation of SAR data. We can then use this representation, we feed it to a very simple model that we see does very good predictions. In fact, these results are very promising, and they are very promising because they have great implications. They can allow us to handle the few labels, this label scarcity, but also it can allow us transferability. We can transfer to different areas the same model for Hokkaido, for Puerto Rico, for Indonesia, and also to different tasks. So not only landslide detection, but also maybe flood detection. It can also allow us to use different bands of satellite. So we can use the C band and the L band that passes better through the vegetation. So after this work, we can be hopeful of a future that when a disaster strikes again, we will be more prepared. Together with Sentinel-1, we will also soon have NISAR. NISAR is a satellite that will be launched by NASA. It will operate on the L band, which passes through the vegetation, and for example, is better suited for Puerto Rico. And it will produce huge amounts of freely available data that then we can feed to our AI algorithms, like the ones that we saw today. And the results of those can inform interventions. And with that, thank you for listening.